Hello class, welcome to Math 111, the online section, and the first lesson. So these first couple of lessons are mainly going to be review. So they're likely to be a little shorter than most of the other videos will end up being. This is stuff that you probably should remember from some previous classes. And this is mainly just a refresher. So for those of you who want to just kind of skip to the homework or the quizzes in this particular chapter, which is chapter P in your book, and do the homeworks and see how you get along with it, I really can't blame anyone for wanting to do that, since this is mainly review material for the most part. But for those of you who need a refresher, maybe need some more explanation or would like better explanation to kind of help with your refreshing, then stick around, because that's what these first few lessons are going to be. Alright, we're going to start our review with exponent rules. These are rules that are pretty important for what we'll be doing, and people tend to forget them. So the first one we're going to talk about here is the multiplication rule. So these rules here, if we have the same base, so in this case I'm using x as my base, and we multiply two things that are same base, different powers, we add those exponents. So for example, if you have, let's say x squared times x cubed, this would be equal to x to the 2 plus 3, or x to the 5th. Okay. The next rule we have is when we divide two things with the same base and different exponents, we subtract those exponents when we use division. Okay, so in this similar example here, if I took x cubed and divided it by x squared, that's going to be x to the 3 minus 2, which is x to the 1. Or just x. Okay, and then this third one we have here is a power to a power. Okay, when you have something to a power and the whole thing's raised to a power, you multiply the exponents. So for example, if I had x squared to the 3rd, that would end up being x to the 2 times 3, or x to the 6th. All right, the next idea we're going to talk about is that exponents distribute. Meaning that if I have, say in this example, three things multiplied together, 2x y squared, or 2 times x times y squared, and I raise the entire thing to the 3rd, that third power distributes to all three. All right, so this will end up being 2 cubed times x cubed times y squared cubed, which we saw in the previous example. When we have y squared cubed, that's going to make that y to the 6th, or y to the 2 times 3. Okay, so 2 cubed, well, 2 cubed is 2 times 2, which is 4 times 2, which is 8. X cubed, y to the 6th will be our final answer. Okay. Exponents distribute across fractions as well. So if we have a fraction, like we have here, x times y squared all over z, and we raise the whole thing to say the 5th, that exponent distributes to all the pieces in the fraction. Okay, the top and the bottom. All right, so this is going to end up being x to the 5th times y squared to the 5th, if we want to write it out explicitly here, all over z to the 5th. And then this y squared to the 5th is going to become y to the 10th. All right, next up are negative and fractional exponents. Negative exponents are fractions, essentially. Okay. This one is actually both of these are super important. For those of you going on to calculus, you'll be using this idea a lot, that negative exponents are pretty much fractions. Right? What that means is if I have x, let's say, to the negative 5, okay, that's the same thing as 1 over x to the 5. Okay? And why might that be? Well, the reason that works that way is remember, when you divide, you subtract exponents, right? And you might be thinking, well, we don't have the same base here. But if you remember, anything to the 0 power is 1. So 1 is actually x to the 0. So what we have here is x to the 0 over x to the 5, since anything to the 0 power is going to be 1. Or I should say anything other than 0 to the 0 power is going to be 1. So if we use that subtraction rule, right, if we divide two things, we subtract their exponents, we're going to get x to the 0 minus 5, which is x to the negative 5. Okay, so that's why that works that way. What you can imagine with this, say x to the negative 5, if you imagine x to the negative 5 being over 1, what a negative exponent does is it flips whatever the base is, right, and changes it to a positive value. So x to the negative 5 becomes 1 over x to the 5th. If we instead had something like 1 over x to the negative 2, so if we have a negative exponent already in the denominator of a fraction, it actually flips back up to the top, okay, and becomes x to the positive 2. And this happens in the same reason as we saw up here, that 1 is technically x to the 0. And when we subtract our exponents, we get x to the 0 minus this negative 2, which comes out to be x to the positive 2 when it's all said and done. Okay, so a negative exponent, just remember, it essentially just flips whatever you have around the fraction bar. And if there isn't a fraction bar, remember you can always introduce one with an over 1. Right, and then the next piece that I mentioned was fractional exponents. And fractional exponents, okay, this camera will focus, that's pretty much the same thing as roots. You might be thinking, roots, what do you mean? Like square roots? Yes, square roots. But it doesn't have to just be square roots. It could be cubed roots. Okay, etc., etc. So our most famous root is the square root. So the square root of, let's say, x, that's the same thing as x to the 1/2 power. Okay, we don't usually put in the 2 here, but you can sort of imagine it's there. We usually leave that 2 off because it happens so often. But next one is the cubed root, which is the same thing as x to the 1/3. The fourth root, which is the same thing as x to the 1/4. The fifth root, which is the same thing as x to the 1/5. Okay. So remember, negative exponents are fractions. Fractional exponents are roots. Now you might think that seems a little counterintuitive, but you just need to remember with exponents it's kind of opposite, right? The negative exponent gives you a fraction, while a fraction exponent gives you a root. What this means for us, though, is that the square root, the cubed root, the fifth root, all those operate in exactly the same way as powers do. Okay? So what that means is that roots distribute. So if you have x, y over z, and we're square rooting that whole thing, shift this over a bit, that square root will apply to every one of these pieces. So this would be the square root of x times the square root of y all over the square root of z. Okay. Same thing if we're multiplying a bunch of stuff together, right? If we have, I don't know, the square root of 4x squared y, y, that's fine. Okay. That square root can apply to each piece individually. Right? So this would be the square root of 4 times the square root of x squared times the square root of y. And I'm sure you all know some of these simplifications, that the square root of 4 is going to be 2, square root of x squared is going to be x, and the square root of y, well, we can't really simplify that much further, that's just the square root of y. And we do need to be a little careful here about the square root of x squared thing being x. I'll get to that. We'll talk about that a little later. For now, just what I really want to focus on is that we can distribute those square roots, or really any root, like we can a power. All right, so what about fractional powers that aren't just a 1 over something? So we have a x to the 2/3, something like that. Well, what I want to do first is kind of go in the opposite direction. So let's say I have something like this. Say I have the square root of x to the 5th, something that the square root does not naturally cancel, like square. Okay. Well, sorry about that. Sorry about any camera jostling. Remember, the square root is the same as the 1/2 power. So this would be x to the 5th all to the 1/2 power. Okay. Now remember, now what we have is x to a power to a power. So whenever we have something to a power and that whole thing raised to a power, we multiply those exponents. So this would be x to the 5 times 1/2. And 5 times 1/2, well, that's 5 over 1 times 1/2. So that's x to the 5/2. Okay, so x to the 5/2 is what we got when we simplified or messed with the square root of x to the 5th. So this top part of the fraction, the numerator, is what x is being raised to, and this denominator is what type of root we have. So given that, if we go in the opposite direction here from x squared, or x to the 2/3, this would be x squared all to the 1/3. Right? We can break that up in this other direction, which means what we have here is the cubed root of x squared. Okay, so a fractional power outside of just 1 over 2, 1 over 3, stuff like that, ends up being a combination of a root and a normal power. So for example, if you have x to the 10/11ths, for example, the denominator is going to give us the root, and the numerator is just the power of x. So this would end up being the 11th root of x to the 10. Okay. If you had y to the 8/5, well, remember the denominator is going to give us the type of root we have, so that would be 5th root, and the 8, the numerator, will give us the power that we have. Okay. And this can go in either direction. For example, one really common problem that you'll probably see is something like, let's say 8 to the 2/3. All right, that's a type of problem you might see in homework for this section. The way to handle this is you can do it in either order. You can either square 8 and then take the cubed root, or you can take the cubed root of 8 and square it. Okay. So I think, just looking at it, I think the quickest way to do this is just take the cubed root of 8. The cubed root of 8 is 2, and then square it. So we end up with 4. Okay. Can we do it the other way? Well, yes. 8 squared. Whoops. Sorry, multiplied by 2. 8 squared is 64. And now we have to think about what is the cubed root of 64. So that might not be as simple as finding first the cubed root of 8. Okay. Also, being able to move different types of roots and things into fractional powers is super helpful, especially if you want to use your calculator. So for example, if I just put this over for a second and say that I want to find, say, the 10th root of, let's say, 5 to the 6th, something like this. Okay. Well, off the top of my head, that's not going to be that easy to do, but if I remember that this is going to be 5 to the 6 over 10, so remember the root gives me my denominator, the power actually gives me the numerator, denominator comes from the root itself. Now, this fraction, 6 over 10, can actually be simplified. We can take 2 out of both of those and get 3/5. So, first of all, that changes the problem a little bit. And doing it in this way means that we can actually use our calculator. Because as long as I use parentheses, right, I can put this fraction in verbatim as 5 to the 3/5. Right, and we get this kind of messy value here, but we still get something, right? Whereas trying to put the 10th root of 5 to the 6th in our calculator would be kind of unwieldy, and there, I believe, are commands for general roots in your calculator, but it's much easier to do things like this using the fractional exponents instead. Alright, to continue, let's look at just some examples that put a bunch of this stuff together. Some things you might see in your homework. So for our first example here, be negative 5x to the 4th y all times negative 4x to the 7th y to the 6th. Alright, so we're going to be multiplying all of this stuff together. And how I like to do it is put everything together, because remember, we can multiply in whatever order we want. So I'm going to put the constants together, the x's together, and the y's together, and be very careful. Remember, I have 2 negatives here. So it's going to be negative 5 times a negative 4, okay, times x to the 4th times x to the 7th times y to the 6th. Okay, and then I go through and just apply all the rules that I know, or you know, whatnot. So negative 5 times negative 4 will be a positive 20. X to the 4th times x to the 7th. Remember, we add exponents. So that'll be x to the 4 plus 7. And then here, y times y to the 6. Well, remember y, we don't always write it, but there's an invisible 1 here. So this will be y to the 1 plus 6. Okay? So this will be 20x to the 11, y to the 7. Alright, next up is going to be 8x to the 1/5 times 2x to the 1/2. Alright, to multiply these, since these have different denominators in our powers and whatnot, we're just going to use the same exponent rules and ideas we used up here for this example. So for this next example, and I'll fix this up a little bit. Okay. So once again, I'm going to write everything out via multiplication. So it will be an 8 times 2, then an x to the 1/5 times an x to the 1/2. Okay, so 8 times 2, that's 16, actually this time. Then remember, when we multiply these guys with the same bases, different powers, we add exponents. So this will be 1/5 plus 1/2. Okay, so this is a good example because it will help remind you of how we add fractions with different denominators. Remember, we need to get a common denominator. Our common denominator here is going to be 10. Now let me show you a quick way to do fractional arithmetic if you don't want to take the time to actually find a common denominator and multiply it out, because over here, this 1/5 plus 1/2, what you're supposed to do is find the common denominator, and they'll fuss at you about finding the least common denominator and all that jazz. One thing you can always do is you can always just multiply the denominators together, right, to get a common denominator. But the idea is they always tell you that you're supposed to do stuff like this, where you multiply the first fraction by 2/2, and then you multiply the second fraction by 5/5, then simplify that out. This would end up being 2/10 plus 5/10, so we end up with 7/10. Alright, and that works, that's fine, but one thing you can always do that will always work, and you might have to simplify it a bit, but you take this first denominator and move it up here and multiply it with this numerator. Okay? Then you take this denominator and multiply it with the opposing numerator. So students like to call this cross multiplication. You can call it that. And then on the bottom of the fraction, you multiply the two denominators together. So what ends up happening is you put 2 times 1 here, you keep your plus sign, make it 5 times 1 here, and put it all over 5 times 2. And what you'll end up seeing is you get a 2 plus 5, if I would actually do it on the screen, a 2 plus 5 all over 10, which is exactly the same result we got doing it the sort of magically multiplying by the funky version of 1 idea. And this idea will always get you the right answer. You might have to simplify what you get at the end. Okay, it might not be the simplest form, but you'll get there. Okay, so all of that is to say that this final answer here comes out to be 16 times x to the 7/10. That's that. All right, next up is 25 x to the 8th times y to the 4th, all to the 1/2. So here, this is basically taking the square root of all of this stuff. Okay, so what we're going to do is distribute this power across all of our pieces. Okay, so this will be 25 to the 1/2 times x to the 8th all to the 1/2 times y to the 4th all to the 1/2. Okay. Now 25 to the 1/2, if you can't think of that right off the top of your head, remember that's the square root of 25. That's end up being the same thing, okay, which will be 5. And remember, with these two, we multiply. Since it's x to a power, y to a power, we multiply. And when we multiply sort of our normal numbers with fractions, right, 8 times 1/2, well, the 8 and the 2 are going to cancel and leave a 4. So this is essentially just x to the 8/2 times y to the 4/2. Okay, so we're going to end up with 5 x to the 4 y to the 2. That's that. Okay, next up, let's try the square root of 9x squared times the square root of 72x. So a lot of ways we can do this, and I think the biggest problem with a lot of these exercises is there are a lot of different ways we could go about it, and what simplify means can mean a lot of different things to a lot of different people. Okay, so a lot of times you have to carefully read what the directions say. So the directions for this particular problem that I grabbed this from said to use the product rule to simplify the following expression and assume that variables represent non-negative real numbers. Okay, then right underneath where you can put in your answer, it says type an exact answer using radicals as needed. Okay, so using radicals as needed means we don't want to have our final answer have fractional exponents, so we're not going to try and move things to be fractional exponents. What we're going to do instead is these square roots can affect each piece individually. So that's what I'm going to do. I'm going to let this square root distribute to everything. So this will be the square root of 9 times the square root of x squared times the square root of 72 times the square root of x. Okay, and then go through and simplify as needed. Square root of 9 is going to be 3. The square root of x squared is going to be x. Now we get to some issues. The square root of 72, well, that does not come out to be a perfect square. In fact, if you go to your calculator and do the square root of 72, you get this. Okay? So, whenever that happens, what we're going to do is start seeing if there's anything else we can take out of it. So 72. If you remember your prime factorization stuff, if I divide a 2 out of 72, we get 36. So what that means is the square root of 72 is the same thing as the square root of 36 times 2. Okay. Then square root of x is square root of x. So using our same rule that we just used before, square root of 36 times 2 is going to be the square root of 36 times the square root of 2, and all times the square root of x. Okay? Now the square root of 36, that's useful because that's going to be 6. Okay? So we'll have 3x times 6 times square root of 2 times the square root of x. Okay. So, bringing all this together, this 3 times 6 is going to be 18x square root of 2 square root of x. Now, I'm going to say there's not really a standard way to do this. You could leave it like this, 18x square root 2 square root x. You could also bring these two together to make it square root of 2x, like so, 18x square root of 2x. Unfortunately, the problem with this all being online, it's hard to tell sometimes what MyLabs Plus is actually looking for. But to me, I think this might be the nicest version. Looking at the solution set, it has it as square root of all 2x. Okay, so if you feel like you got the right answer and you have these separate square roots that can't be simplified down, try and bring them together as a single square root and see if it doesn't fuss at you anymore. Alright, next up, let's look at negative 10 x to the 10th y to the 5th all over 2x to the 5th y cubed. Alright, so this problem says simplify the exponential expression. Then the directions actually say simplify your answer, use positive exponents only. Alright, so let's see if we can do that. There are, again, many ways we can go about this, but one thing that I think is helpful, remember when we multiplied stuff, we grouped everything, we grouped all the constants together, the different variables together. We're going to do the same thing here. Okay, we can actually split a fraction up with multiplication, so that this would be negative 10 over 2 times x to the 10th over x to the 5th, then y to the 5th over y cubed. Okay, now we can only do this if it's multiplication. Okay, only multiplication works this way. Alright, now we're going to go through and apply all our rules that we know. Okay, so negative 10 over 2 is negative 5. Now, when we divide things to exponents, remember we subtract. So this will be x to the 10 minus 5. And then, once again, we're going to subtract. This will be y to the 5th minus 3. Okay, so we'll get negative 5. And this will be x to the 5th times y squared. Okay, and there we go. We've simplified this expression, and we've used positive exponents only. Bam. Alright, next up, let's try square root of 48x to the 5th all over the square root of 6 times x to the negative 1. Alright. This one, there are many different ways we could go about doing this one. Okay. The first would be to maybe distribute the square root to everything. That might be a little problematic, but that's one option. We could change all those square roots to 1/2 powers and apply it to everything. Or, and I think this might be the best option here, these two square roots, square root of the top, square root of the bottom, can actually become the square root of the entire fraction. All right, so this would be the square root of 48 x to the 5th all over 6x to the negative 1. Because remember, if we can go one way in math, we can always go the other way. I maybe shouldn't say always, but with everything you've learned so far, you know, with minor caveats aside, you can usually go in whatever direction you want. So remember, if we had started here with the square root of some fraction, remember we could just distribute that square root to the top and the bottom. Well, if we already start with the square root applied to the top and the bottom, we can just apply it to the fraction as a whole. Now, how does this help us? Well, it helps us because what we can do now is split things up in a way we could actually use. Okay, so this would be the square root of 48 over 6 times x to the 5th, or x to the negative 1. Okay, and doing it this way means that now we can approach it like we did before. Remember the last problem, we had split up the fraction and did each piece separately, the constant piece, the x piece, and then we were done. Well, now we're going to do the same thing, but then we can apply the square root to everything once we're finished. Okay, so here we go. 48 over 6 is going to be 8. And remember, we're going to subtract exponents here since we're dividing. So this will be x to the 5 minus negative 1, just to write it out explicitly. Okay. So that will be x to the 6th. Right, so in total we have the square root of 8 times x to the 6th. Right, so let's apply that square root to both pieces. Right, so this will be the square root of 8 times the square root of x to the 6th. Now to do both of these pieces, we're going to approach them in different ways. All right, first of all, to do this square root of 8, and MyLabs+ typically wants you to do this, is to break things down as far as you can. But square root of 8 isn't something that's just super nice to begin with. But remember, if over here, if we take a 2 out of 8, we get 4, and 4 is a perfect square. All right, so what we can do is rewrite this as the square root of 4 times 2. What we're going to do for this guy here, this x to the 6th to the square root, is we're going to change that to the 1/2 power. Okay? And in doing so, what we end up with is, now we can break this up. So it's the square root of 4 times the square root of 2. Then this is going to be x to the 6 halves, because it's x to a power, so we're going to multiply those exponents. Or it's going to be, as we talked about earlier, the square root of x to the 6th. We can actually skip all this and think, oh yeah, the root is going to give us our denominator, that power is going to give us our numerator. So we can go straight from here to here, but you remember that. Okay? Square root of 4 is 2. Square root of 2 is, well, square root of 2. I can't really do anything with that. And x to the 6 halves. Well, 6 halves is 3. Okay, so our final answer here is 2 square root 2 x cubed. Often, just as conventions, a lot of times square roots are moved to the back. So I guess they look better there. MyLabs Plus should count this correctly. If it doesn't, let me know. I think that's one thing I want to make clear. If you feel like you got the right answer and MyLabs Plus is marking it wrong, and you think it's only marking it wrong just because of like a clerical error, like just the order you write multiplication in, just email me. Tell me what assignment it is, what problem it is, and I'll take a look at it. And if it's correct, I'll give you the credit. And if it's not, I'll tell you why it's not. Alright, for this one, let's try something a little different. Let's say we have the cubed root of negative 1/27. Alright. First of all, some of you might be thinking, well, we can't do that. That's not a real number because we can't take a root of a negative number. And I would say to that, be very careful. We can take a cubed root of a negative number. We cannot take a square root of a negative number. Okay? And that comes from the fact that even roots will cancel out negatives. So if you have a negative x squared, that's negative x times negative x. And negatives cancel. And you can't even see what I'm writing here. If you have negative x all squared, it's going to be negative x times negative x, which those negatives cancel and gives you x squared. The negative cancels. But if you have negative x cubed, right, these negatives cancel, but then we're still left with 1. So it preserves the negative. And because of that, roots preserve negatives for odd powers. Okay, so this, a cubed root, okay, of a negative 1/27th is going to be negative the cubed root of 1/27. We can just take that negative sign outside. If, on the other hand, I asked you to find something like what's the square root of negative 4, well, you could say it's not a real number. But a cubed root, or a fifth root, a ninth root, any odd root, negatives will work. Okay. Now, from here, we can apply the root to the top and the bottom. Right? Because I think what happens is some students will actually just try and think off the top of their head, oh my god, what is the cubed root of 1/27? And they get so hung up in what, you know, the idea is trying to do it all at once. But you can always just apply your rules. Just apply it step by step and distribute that cubed root to the top and the bottom. So remember that negative on the outside. This will be the cubed root of 1 over the cubed root of 27. And now things are a little more manageable. The cubed root of 1 is 1. The cubed root of 27 is 3. And there we go. There's our final answer. Okay, so take a look at how I did this problem. Every example I've done so far, as they ramped up in difficulty, I didn't just try and get the answer in my head or try and just brute force my way through it. I step by step applied rules that I knew, the first ones that came to my head, and just did them carefully until I got down to just having a final answer. And that's what's going to help you with these problems here. Alright, I think that should be enough to kind of get you started on the homework. Remember, feel free to email me with whatever questions you might have. This first lesson may have seemed a little fast, disjointed. Things will start to get a little smoother as we go along. These review sections are kind of going to go at a bit of a quick clip, mainly just by the based on what they are. Okay. But if this felt a little fast, keep in mind it's mainly just because it's review. I will say if this felt like things you've never seen before, and you're having a lot of trouble with this early stuff, this chapter P stuff, please contact me, because that's not a great sign. I don't want to discourage you, but this should feel more like a refresher than something brand new. Alright, thanks for your time, and I'll talk to you all on the next lecture. Cheers.